So, a couple things. You know when you have a tummy ache, sometimes you take some medicine to make you feel better. Can you name any medicine that you take that makes you feel better when you have a tummy ache? Pepto-Bismol and Tums and things like that. Those things are bases. What's in your tummy? Hydrochloric acid. So if you have too much acid in your tummy, you can take a base and it'll make you feel better. Now that's called neutralizing. Neutralize. Okay? There's a real simple formula for neutralization. And that formula goes like this. An acid plus a base makes salt and water. And you're like, what? Is it really that simple? Yeah. The answer to that question is yes. It really is that simple. Let me show you the most classic example of a neutralization reaction I could show you. Check this out. Here's your classic acid, hydrochloric acid. Here's your classic base, sodium hydroxide. Let's do a double replacement reaction here. The sodium will be with the chlorine. Isn't that salt? And the OH would get with the H. Or the H would get with the OH. What's another way to write HOH?
H2O.
Yep. So that is a classic neutralization reaction. Okay? Neutralization means you bring the pH to 7. If you totally neutralize it. Does that make sense to everyone? Okay. Now, you know that if you had like a whole bucket full of terribly strong hydrochloric acid, that you couldn't put a couple of drops of base in there and neutralize it, right? It has to be even amounts, or even amounts and even strengths. Does that make sense? So, knowing that, we can actually use our brains in a simple math equation to discover the molarity or the pH of unknown substances. Well, what do you mean? Well, there's a couple of steps to this, okay? There's a couple of steps. Step number 1, we can use what's called an indicator. You want to write this word down. An indicator. An indicator is a chemical that changes color due to pH. All right? And Lord knows there are many, many different indicators in the world. I'm going to show you a list here of some indicators, and you're going to be like, what? Check this out. Here is a list of indicators. And if you look at the bottom, here's the pH, 0 to 14, okay? So if you work somewhere and you're working with solutions and you need to see if their pH is, say, for example, 2, you need to know exactly when the pH changes to 2. You could use this indicator right here called methanol yellow. And if it's yellow, it's above 2. If it's red, it's below 2. You see the color change right on the number 2. Does that make sense? The indicator that we use in here changes colors exactly at 7. And it is called phenolphthalein. Phenolphthalein. I always look this up to spell it because it's pretty crazy. But phenol, I'm serious, I'm not joking. I looked this up. I looked it up earlier today. Phenolphthalein. Here we go. Phenolphthalein, like Daffy Duck wrote this. All right? Phenolphthalein is an indicator that we use, and it is pink in a base, and it is clear in an acid. So it changes color perfectly at 7. And it is an excellent tool for us to use if we want to actually neutralize something. Does that make sense? We can see when it turns from pink to clear, or it turns from clear to pink, and boom, right then it's 7. Does that make sense? If it's pink, it's at 7.01. If it's clear, it's at 6.99. Right? So, what is an example of how we could end up using phenolphthalein to discover the concentration of an unknown solution? Well, we'll do an example in here, and this process is called titrating. So the last thing I want you to do real quick is write down this term, titrating, titration, or titrating. We're going to be titrating a solution, or in other words, titrating a mystery solution. And the formula is a formula you've already used. It's the dilution formula. M1V1 equals M2, you're missing it, Taylor, M2V2. So this is the formula that we're going to use here to titrate, all right? Now, except for this, instead of diluting something, over here we'll have either the acid or the base, and over here we'll have either the base or the acid. So if we know the molarity and the volume of one of the substances, and we can calculate the volume of the other, then we can solve for the thing we're missing. Does that make sense? So we're going to have a formula like this, and we're going to be able to get 3 out of the 4 variables, and then do some algebra 1 to solve for the other. We're going to do what's called a titration. So what I have here is all the stuff we need to do a titration. And titrations are really simple. M1V1 equals M2V2, R2D2, C3PO. Yeah, it's a joke. M1V1 equals M2V2. If you didn't get that joke, all right. So, let's think about this. Here is a known solution, okay? I have some sodium hydroxide, and you can see the strength. It's 0.05 molar sodium hydroxide, so that's good, right? We know about this. So now we know the strength of this, so let's use a known volume, okay? So I'm going to use this little graduated cylinder here, and let's see. I'm going to use 40 milliliters of it, okay? So, I've rinsed this out. I've got 40 milliliters of 0.05 molar solution, all right? So, let me write this down for the kids at home. Because if I write on the board, it's not going to quite work the same. So, we're going to do this. M1V1 equals M2V2. All right? Here, everybody see this? People at home, you see this? Right? So for the sodium hydroxide, we have 40 milliliters, and the molarity is 0.05 molar. Okay? So we have 2 of our 4 variables already. We've got M1 and V1, right? Okay. Now, if you look very closely, you will see there's a clear liquid in here. And the clear liquid in here is hydrochloric acid. But you don't know anything about it. This could be very strong and very dangerous, or it could be very, very weak. We don't know. It's a mystery. Okay? But what we can do is use it to titrate this stuff that we know about. Now, remember I told you phenolphthalein was an indicator, and it turns pink in a base. And sodium hydroxide is a base, so watch this. 1 drop, everybody. Boop. Pink, isn't it? Isn't that crazy? So phenolphthalein is just like the chemical that's in hydrangeas and other flowers that change color depending on the soil they're in. Phenolphthalein is pink in a base, and now we know that that's a base in there. We know the strength. We know how much of it there is. We know the volume. I'm going to put this behind it, and this might help you see the color. Does that help? All right. All right. So we've got. So we've got this pink stuff here, and if you look very closely at this, you can see it's graduated, or it's got marks on it. So what I'm going to do is I'm going to drip this into here until this changes color. The second it changes color, I'm going to stop dripping it. And then I'm going to read these lines and see how much I've used. Then I'll know the volume of the hydrochloric acid. Does that make sense? Now, we're starting, jot this down, Jalen. We're starting right now at 13.2. And kids at home, that number's not important to you. I'm just going to see the difference between 13.2 and where we go, right? And the difference in where we start and where we end, that's the volume that we're going to write down. Does that make sense? You wrote it down for me? All right, let's get this party started. I'm going to start, when I drip, you drip, we drip. I'm going to start dripping. And we're going to look for, whoa, that's too fast. At home they can't see this, but you kids can see it. All right, so I'm dripping, swirling, swirling. I'm swirling it to mix it. We're looking for that color change. We're looking for it to go clear. As soon as it goes clear, I'm going to stop. This is titrating. And actually, you would really, if you had a really doing your best here, you would go much slower. I'm going drip, 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 drip. I'm going faster than you would go. Okay? Swirling, swirling. What are we looking for? Yeah, we're looking for it to all go clear. And I can see from my angle that when it hits, it goes clear for just a second. So I know we're getting close. Clear. Nice. We titrated it. Does that make sense? So we went from 13.2, and now we're at 20.6. So we went from 13.2 to 20.6. 20.6 minus 13.2 means that we use 7.4 milliliters. Does everybody agree with that? This was the new number. This is the original number because we're just reading it backwards, okay? So the difference in those numbers is 7.4 milliliters. So we dripped out a volume of 7.4 milliliters. 7.4 milliliters. So now we can solve for what? That's right. Now we can solve for the molarity of that acid. All right? So we have 0.05 times 40 is equal to M times 7.4. So let's solve for that molarity real quick. We're going to cross multiply. .05 times 40 equals M2 times 7.4. So we're going to say 0.05 times 40 divided by 7.4. That's how we're going to cross multiply. Right? Does that make sense to everybody? Just cross multiply. We're just solving for the one letter that we're missing. 0.05 times 40 is equal to M2 times the second volume. So 0.05 times 40 divided by 7.4. What'd you get? 0.27. Everybody agree with that number? Before I show it on the video? Have you done it?
Yeah, I put 0.3, but
0.27. We're going to try to keep some distance. So 0.27 molar HCl. So the molarity of that acid was 0.27 molar, right? And now you know what's crazy? You can tell me the pH of this acid. What two buttons do you need to hit? You know the molarity is 0.27 molar HCl. What two buttons would you hit? Log negative. Hit log negative for me. What's the pH of it? Huh?
0.57.
So the pH is equal to 0.57. Now we normally don't go all the way to pH in these problems, but this is what we've been doing today. So everybody at home, we used phenolphthalein indicator to titrate this solution. We already knew the info about the sodium hydroxide. We had 40 milliliters of 0.05 molar. Then we calculated what volume of this we needed, and that way we solved for how strong this acid was. Does that make sense? That's titrating, and that's titration math.